In January 2015, the first State of the Bay Research Symposium was held at the Alaska Ferry Terminal on Bellingham Bay. The purpose of the all-day event was to enhance communication and coordination between various agencies, organizations, and citizens involved in the protection of Bellingham Bay. The symposium brought together researchers, managers, and interested citizens who are all connected to the future of the bay. The symposium featured 7 distinct topics, including Bellingham Bay Yesterday and Today, local key issues, challenges, and research needs, physical processes, chemistry and water quality, biological ecosystems, regional research perspectives, and moving forward with limited funding. We will present the State of the Bay Symposium in 7 parts. This is Part 3, Physical Processes.
Well, thank you all for coming. Thank you for hosting all of us. This is fabulous. We're going to try to describe what happens with a lot of the flow coming down the river, the mixing of the ocean, fate of sediment as it mixes into Bellingham Bay, and how it's influencing our coasts and some opportunities for restoration. This picture is a typical picture out in Bellingham Bay. The heavy turbid plume of the river. It's probably much more pervasive nowadays for reasons that Bert and Randy described, with a lot more sediment coming down. So you'll notice this throughout. I'm going to talk a little bit about what that sediment and the replumbing of the whole watershed, as well as plumbing along the coast, has done to our habitats. We're going to follow up with Mark's talk that's showing some interesting linkages of nutrient transport, some of those with sediments. Tarang will be talking about the circulation model that PNNL has and has been used in Bellingham Bay. And this is one of 2 other large-scale Salish Sea hydrodynamic models that are being developed currently. One by the UW for looking at how ocean mixing occurs and influences ecological processes, and one that the USGS, my team, is developing with Delft3D, largely to force smaller nested models at specific locations like the Elwha to look at dam removal, and a number of our delta sites that you'll hear about today. And then Jim Johannessen will be talking a lot about some of the coastal change analysis that have been gone on here in Bellingham Bay and nearby, and how it's being used to assess priorities for coastal restoration. I'd like to acknowledge a few folks. I bring an interdisciplinary team of hydrologists led by Chris Curran, fishery biologists led by Steve Rubin, and geographers who do some socioeconomic work, including Bill Labiosa, from our USGS team, but a number of partners over the last 6 or 7 years listed here. And so today I want to talk about some of the importance of the hydrology and the sediment transport and its linkages to some of these issues we've heard about. Impacts to habitats, natural hazards, and some of the change. How we're now developing some climate change downscaling tools to look at these impacts in the future and follow up with some information needs. So initially, our work was geared to address salmon recovery and Puget Sound recovery with the plummeting populations of salmon that you've heard about today. And a large part of this was figuring out how do we deal with this landscape that has been transformed from one that used to have rivers, in this case the Skagit, flowing over an enormous area, and now is entirely replumbed to move all that fresh water and sediment from this area here down through these channelized systems that focus it like a fire hose out these 2 systems. This is much like research to support dam removal. We're talking about dams that are controlling tens of thousands of acres that are proposed for restoration around Puget Sound. So we quickly realized that part of the question is how to restore some of these estuarine systems here shown in the oranges. But another part of it is what the impacts of forcing all that material out across our nearshore. And you'll see that disturbance in just a minute. It's so evident in this photograph from the Skagit where the river has been focused right here beyond the shoreline. We have these braided complexes of river channel extending all the way out 5 to 8 kilometers offshore, disturbing chronically these eelgrass beds that used to extend all across this area. Notice the middle part is much more different. It's a lot less disturbed, but somewhat disturbed. And this whole area now has subsided by a meter or so because of less sediment delivery to the floodplains. Areas here are being starved from sediment because it's just not routed there anymore. And then these areas are chronically disturbed and are critical for salmon recovery. We're finding new information that Chinook salmon prefer to rear in these eelgrass beds shown here for the majority of the summertime. Their fish that they eat, forage fish like herring, occur in much more abundance in those low disturbed eelgrass beds. And the bottom of the food web, all the invertebrates that feed fish and birds are much higher in species richness and abundance in these more continuous, less disturbed environments. It's the lack of chronic sediment moving out across the system, abrading things. Interestingly enough, some of our key targets for recovery, like eelgrass, could be achieved by simply fixing this sediment problem. We estimate about 20% of the partnership's 2020 target for eelgrass could actually be covered right here in the Skagit. Closer to home, here's Bellingham Bay, July 3rd of 2013. The turbid plume is spreading across the entire system, very high turbidity levels. As this sediment moves down through our watershed, it's affecting spawning habitat up in the rivers, more lethal direct influences. This is a chum salmon blinded by high turbidity. Obviously, when sediment accumulates in our channels, it creates more flood hazard and risk. We're finding more and more emphasis on needing to filter out a lot of high turbidity for our drinking water. And down at the shore, marshes and our coastal systems want to receive sediment so they can grow. So we put together a program looking at all 6 of these larger, sort of less urbanized delta systems to better refine how much sediment's coming down, what it does as it travels through the coastal zone and makes its way out into the to its final fate. And a key issue or idea I want you to go home with is that sediments are much more important here in the Pacific Northwest than, let's say, Chesapeake Bay, where we get a lot of guidance, or we look for guidance in terms of how to restore our system. It's steeper, it's much younger geology, it sheds about 20% more sediment down the rivers to our coastal zone. And most important, when you scale the area, which is much smaller here in Puget Sound, for catching that sediment, essentially there's a 5 times greater loading and sort of disturbance level in Puget Sound nearshore environments as that sediment makes its way through the system. So how do we get to the measurements of sediment coming down our systems? We do a lot of work with some really fun new acoustic tools and optic tools, back and forth through channels to measure the flow. We get, in a sense, real time what that discharge is and how turbid it is right then and there. And we're getting to a point now where we can refine our error down to essentially 3 and 4% on the amount of water coming through over a number of different ranges of flow. And then we use these new tools with turbidity that measure turbidity constantly at our gauges. And then we develop rating curves to relate it to the suspended sediment concentration. This gives us discharge loads of sediment now that are much more certain than, let's say, 5 to 10 to 15 years ago. So if we can monitor turbidity for fairly cheap and discharge, so discharge in black over the last 3 years as an example here at Ferndale, we can now calculate the sediment load associated with this brown turbid measurement over time. And this is what the record shows for the last 3 years, and it's very representative of the last 40 or 50 years. About 1 million tons of sediment are coming down our systems, or down the Nooksack, by Ferndale, and about half to a little bit more is the sand fraction of the total load. So where does it all go? We have some tools now that we use to look at the nearshore environment. And this is seafloor mapping. This is what the data looked like when we began the project, and it's really poor right in the nearshore environments that we care so much about for shellfish, eelgrass, what have you. All of these big fat polygons are simply errors and biases of interpolating no data or very old data. So in a very nice collaboration with Lummi, NOAA, and a few others, we've merged some new topographic LiDAR that was collected in 2008 with some existing NOAA data and some new sonar data that we collect to fill in this gap, looking at bathymetry and habitats like seagrasses, shellfish areas. And then we bring some of these shallow water tools up the rivers to look at sedimentation in the rivers. I want to show you a few examples of what this looks like. This is the new sort of digital elevation model that helps us plan and assess what's out there. It's tremendous. Some of the detail here is just incredible for essentially detecting sands moving across the system and down the face of the delta constantly. And we'd have multiple years showing this, as well as slumps that are kind of hazardous if they were large enough to create a local tsunami. But we do have two other older data sets, 1880 from the earlier NOS measurements. This is what the delta looked like back in 1880. And I'll forward to 1956. They didn't catch all of it, but they did catch the outer area of the delta. And then back to today. It's pretty striking just how much progradation of that tidal flat occurred over those years. Now we can difference those and calculate the thickness and the change between 1880 and 1956 shown here, directly from those two data sets I gave you. And we calculate over 76 years that about 250 of these million cubic meters of sediment came out at least and were stored in this portion of the delta. And if we move to this last 50 years, you can see how it just shifted seaward to fill in again offshore. The last 55 years, it's about the same total amount, but because it's a shorter period, we actually appear to have more sediment, 350,000 cubic meters collecting here in the last period. So in fact, maybe more is coming out. We also have, at an annual time frame, some change analysis from our surveys of these same environments. And it shows that there was about 30 to 40 meters of tidal flat progradation in just 1 year between 2010 and 11. And again, very close to the same number I showed you for the decadal scale change, 300,000 cubic meters in just this one little area. We think that's mostly the sands. The muds are getting swept even further away. So here's the net change from 1880 to present. If you draw a line through it, here's what happened. A kilometer and a half of progradation, a major steepening of the slope, which again can be a hazard. We calculate the total amount, and we can now relate it to the amount of sediment we calculate coming down the river over those same years. And it's about 47% of the total load, 97% of the sands. So I think we're doing pretty good at quantifying where the sands go. The rest of this mud fraction, again, swept offshore, creating beaches in places that used to be white sandy beaches from a number of stories and are now covered in mud. But this decrease in slope is likely to have a major influence on flooding and other issues up above in the system, including drainage of ag fields. But we don't have much data from the past to compare how flows and routing through these distributary channels have occurred. But we've begun to measure this. This is an example in 2013. Majority of the flow coming down to the delta is now moving out through the west distributary along the Lummi reservation. Very little going down here. We think this is quite different from just a few years ago. There's a massive log jam I'll show you, and this entire channel has filled in just 5 years. This is 2006, Google Earth, beautiful imagery. The majority of the flow was going right out through here along the Bellingham front coastline. By 2011, this entire area is being filled in. It's kind of a trickle these days, except at very high flows. And more than a kilometer of channel has filled in with logs and is essentially closing off this whole system. Now you've got much more flow coming down the west end. This could very well be part of the problem with the fecal bacteria seen at Portage Bay that used to flow out here, and just around this time period is now flowing directly to Portage Bay. Up higher in the system, we're seeing evidence of changing channel bathymetry, essentially this black line that we've measured in 2012 or 13 relative to 2006 in red. And essentially below Ferndale, the entire reach shows aggradation of sediments in the channels on the order of a half to a full 1 meter in just a few years. So if we, again, this then drives human behaviors to need to control floods, build levees, or an alternative, and that and then has major impacts on our coastal zone. So if we think we have an issue with sediments and flooding today, it looks very interesting in the future. This is more work that we've done in the Skagit as an example, but it's very relevant to the Nooksack. This is the Climate Impacts Group downscaled climate modeling of the hydrologic runoff of flows in the watershed of the Skagit. And it's, again, similar to the Nooksack, a major change towards much higher winter runoff and much lower summer low flows, which are going to affect a number of things. Well, this has a pronounced influence on sediment because most of the sediment is moved during the highest floods. When we run these flows in the future through our sediment models, our sediment transport models for that kind of a discharge, we start to predict at least a 3 to 6 times increase in the amount of sediments coming down sort of the North Cascade rivers by 2080. And that's shown here. This black line is today, and the error range of all the general climate models that you hear about, and the median is right here in terms of forcing more flow and sediments. On top of that, you've got sea level rise trapping more of the flow and sediment up into these estuaries and lower rivers, and a number of other processes that we're working on that influence where sediments go. So 2 more slides. We're putting all this together into several types of models to help inform managers. One is at the large scale of the whole Salish Sea. What happens to this sediment? In particular, the fraction that is retained in the emergent portions of our deltas that sort of help us grow and keep pace with sea level rise. That's this little green wedge. It's a very small component of the whole sediment loads for all of our rivers. Most of it's getting forced offshore where it's lost as a resource for us. And then in blue is the potential marsh accretion that could occur given the amount of tidally connected wetlands today where those sediments can route and go and accumulate. And so we're doing pretty good for marsh up here in our area with respect to rates of sea level rise that are on the order of 3 millimeters a year. But in some places much lower and much more vulnerable. So we're now looking at all of these geologic processes, sediments, the way the land moves up and down, tides and waves, how vegetation traps sediment, and restoration opportunities to help guide cumulative effects assessments and where you can put restoration in to reduce flood hazards, large-scale floodplain connections, and estuaries. And all of this is being incorporated into what we call a Puget Sound Coastal Resilience Tool. It's located at the Spatial Institute at Western Washington University. You're all invited to come look at your favorite delta, map out a bunch of information, especially how future sea level rise projections are likely to flood lands, influence our infrastructure, ecosystem restoration, and such. And we want to develop this more with some of these other metrics. So in conclusion, sediment impacts cross-cut a number of issues that we faced in Bellingham Bay and across Puget Sound. It's very tightly coupled to flooding and how we mitigate floods and redirect flows. When we couple it to climate change, it looks like the future is going to be for a lot more sediment coming down because of the way the groundwater and surface water are influencing the debris flows you hear about, the landslides like the Oso slide, and what have you. And then we have these new tools to quantify that change and evaluate opportunities. Some of the information needs that we are looking at, better detection and understanding of just where is that aggradation occurring in our river systems to then help plan what to do. How long does it take for slugs of sediment to move through our lower rivers and estuaries? And then metrics to detect if any of the sediment management that's going on is actually being effective. I think we also are learning so much about how important the nearshore is for not just juvenile salmon, but also shellfish. And use that information to better understand how much we need to regain, but also if there's an opportunity to offset some of the demands on the estuary, we might be able to get some more production of fish in our nearshore. And then there's this idea that we build marshes, build oyster reefs, we can actually start buffering storm surge and waves that are affecting our coast. So thank you for that intro to a number of issues that are going to be raised now as flows and sediments bring more and more material down to our shore. So I'm going to invite Mark from Department of Ecology. I'm not sure. Here we go. He's been doing some interesting work on nutrient relationships and dynamics up in the freshwater, and you can surmise where it's going and what it's doing. Mark?
Thank you. Well, thank you. It's quite amazing just to see how, in context of research, how interconnected our work becomes and how we can sit in a forum and compare our notes together, and it's really refreshing to see that. I was lastly invited just to come on this panel. My focus really is for freshwater quality monitoring, but we're noticing from our long-term records actually some correlations that we're seeing. Differences, though, realistically, from what's Eric's program, he is more of a continuous monitoring. They have some very elaborate models. Our program is based on mainly discrete sampling. There are some correlations there, and there's a little bit of differences, but it's just in the magnitude of data we've been collecting overall. But basically, I just want to briefly touch upon kind of what our background actually is, what we do at Ecology for freshwater monitoring. And a review of a current station that's located 3.4 miles away from Bellingham Bay, which is our closest station. It's the Nooksack River at Brennan. We want to review some of the current water quality trends over a period of record between 1994 to 2013, and then a summary of our seasonal nitrogen and phosphorus concentrations and fluxes. Now, this seems to be driving the water quality specifically at this station from what we've been viewing. Now, in regards to our overall program objectives, what we do, basically we report on water quality for the state of Washington in order to determine which water bodies are actually exceeding water quality standards that are actually set by the state of Washington, but also to evaluate baseline trends. We have an elaborate network of 66 long-term stations with over 20 plus years worth of data, and we've been operating for about 50 years roughly. We collect a series of water quality parameters and constituents ranging from nutrients to turbidity, to suspended solids, standard water quality parameters like pH, conductivity, and temperature, and we also include metals as well. We're looking potentially to expand the program more from a discrete sampling program to a continuous monitoring program, although we do have only a few stations in the Puget Sound region and statewide to do continuous monitoring, which we're planning to expand, actually. We summarize all the data into an indice called the Water Quality Index for reporting. It's a reporting measure, which I will talk about very shortly. In the context, if you're just to narrow it down to Puget Sound, we have 38 stations in the Puget Sound region for a long-term record. 13 of the stations that we have actually has 20 years of data to infer water quality trends, the Nooksack at Brennan being one of them. And what's interesting about this site is usually a part of our probabilistic design is we're trying to place stations for long-term records at the lowest point in the watersheds to actually get the cumulative effects. Now, for a discrete sampling program with a limited budget, you want to just strategically place your stations where you're going to actually measure that through a long given period of time. We do have other stations up in the watershed, Nooksack at Cedarville, which is actually technically a little bit less of a record, but we can try to quantify some upstream and downstream effects, actually. The water quality index that we actually use to report is what it is technically. We take all the parameters that we actually are sampling for and we normalize it. Since different parameters have different behaviors, what we want to try to do is just measure apples to apples instead of apples to oranges and compare everything. So we summarize it and rate it in a scale from 0 to 100, 0 being 0 between 0 and 40 is poor water quality, 40 to roughly 79 is moderate, and then 80 to 100 is basically good water quality. And that 80, that baseline 80 is meets what water quality standards are. In terms of nutrients and sediment, that we don't actually have state criteria set for yet, which however we're trying to work on that. We're basically taking the upper 10% and the lower 10% percentiles for high and low concentrations to measure what's in that scale. Now, the why we do this is basically, we use this as a tool, as a screen. We want to actually find out which stations are doing good and which stations are doing poorly. And what we do on a yearly basis is we'll summarize all the stations, for example, the 13 long-term monitoring stations in the Puget Sound. We'll summarize all the scores up on an annual scale, calculate a regression curve, and then basically try to determine the interannual variability between the years for all stations rolled up. Now, what we've noticed since 1995, since we started using the indice, is most of the water quality is basically in the mid-70s. However, as you progress through time, we notice a slight improvement to 2013. Some stations are improving, while others are not. And when you look at the long-term record, the Nooksack is the lowest scoring station in Puget Sound. We're scoring 57. And we said, okay, well, that's interesting. Well, why is that? So if you break the individual scores down, nutrient and sediment is really driving it. We're scoring in the 40s, 50s, and very low 40s, actually. So there's something going on there with nutrients and sediment, obviously. The fecal coliform issue also has been an issue. There's been some slight improvements through the years, but that's very give and take. We're always averaging something. It's not, and it's also based on 1 point sample. It's not the cumulative effect. So when we do that, we screen out the initial problem parameters and we take a little bit of a closer look at it. And what we've noticed with nitrogen, for total nitrogen, there has been a significant decline in total nitrogen since 1995 to 2013. And it is a significant trend. And this was perplexing to us. We're saying, well, shouldn't that be just the opposite? But actually, it totally has been the case. We looked at it over statistically many times. We even tried to analyze the seasonal effects. Now, what we do is we actually take a combination of heat mapping, and we actually look at the seasonal distributions month by month in difference between 2 decades. So for the first 10 years, from 1994 to 2004, we look at the distributions from January to December, and then from 2004 to 2013, look at the change in the distributions. And what we've noticed that in certain months, specifically in January, April, and July, there are trends there. Significant shifts in distributions between total nitrogen have actually decreased. So that's really interesting. But in an annual context from 1995 to 2013, if you actually calculate the entire loading for the Puget Sound and the contributions for each one of the systems, we found that the Nooksack at Brennett, the Nooksack is the most highest contributor to nitrogen. It's in the top 90 percentile. So you're dealing with a system that really does deliver a lot of nitrogen, but why is there such a decrease? Well, this is interesting. We looked at all the other river systems, and all of them, except 2 systems, are showing the same trend, an overall regional decline in nitrogen altogether, and we do not know why. So even the total flux, we've also seen a slight decrease. So we're asking ourselves, well, what could be possible? Is it most of the nitrogen being utilized within the watershed? However, the story doesn't end there. The same time we've seen the decrease in nitrogen, we have seen a massive significant increase in phosphorus. So as the nitrogen has been decreasing, we've seen more of an uptake or an increase in the concentration and loading of phosphorus in general. And that's by 35%. If you actually tease out the seasonality and for flow, for the confining effects of flow, we've also done mass regressions, and we have come to the same terms. Increase in phosphorus. So if you're to look at the seasonal aspects, where does that change? Now, if you have a decrease in nitrogen and an increase in phosphorus, what are the ratios doing? The N to P ratios at the same time seem to be shifting about that same time period, as well as it's mostly taking place in the summer when you see lower flows. Now, for turbidity, since we're actually grabbing discrete samples, we have not seen a real significant change at that particular station. A slight decline over the years, but not enough to actually infer a real solid confidence. I mean, there's a lot of data showing that in other parts of the watershed, we are seeing severely an increase in sedimentation. Particularly at this spot, based on the discrete monitoring program, we're not taking in continuous data, and we're also not looking at seasonal high flow events. But if you're to make the correlations between phosphorus and turbidity, we see amazingly tight correlation, very, very tight. So phosphorus and sediment are interlinked somehow. And also, but when we look at the nitrogen and actual turbidity, we see a lot more noise in the data, and we're not quite getting that tight correlation. So another thing we were trying to do is look at terms of continuous monitoring data in order for us to take a closer look at that to see if those correlations are more prevalent. But if you ask yourself, look at the changes in flow events, which could be actually acting as a somewhat of a driver. We've noticed that since 2000, and looking at the Ferndale record, if you look at flows above 575 CMS, we've noticed the frequency of flows have totally increased since 2000. So the frequency and magnitude of higher flow events seem to be on the upcrease. And also, look at the spring discharge. Higher increase in flows overall in the spring season. And the overall seasonality, 4.1% in the annual means, 34% in the spring flow increase, and then you have a longer period of extended flows at 13% going into the summer, into the fall. So what does that mean? Well, if you have a shift, a monumental shift in flow events, specifically in the spring and longer summers, you're going to actually have the fate and transport of your phosphorus, your nitrate, and your turbidity are going to change. And what we've noticed in the spring vents under lower flows, that this is basically a summarization of your discharge versus the amount of concentration moved per each month. We noticed actually in the springtime that higher concentrations of sediment is being more mobilized at the lower flows. And that makes kind of sense, because if you were to take particles and move them slowly with less energy, you're going to actually have more dense material associated at one given point in time, which will show up in your sample. And that's moving from spring into summer. But when you look at total nitrogen, we see less of an increase with flow. However, when you look at total phosphorus, that's amazing. Total phosphorus, higher concentrations of phosphorus moving through the channel right into the summertime at those low flows, that means you're going to have a longer residence time where phosphorus is available for biological uptake. So that's a significant factor right there. So more or less, our base observations is, as standard with some current hypotheses in the watershed, is we're likely to experience either spring runoff and prolonged low summertime flow conditions, as well as seasonality in river flows where peak flows start earlier in the year. However, we've noticed turbidity concentrations are much higher at lower flows in the spring. Total nitrogen and flux have decreased, and then higher concentrations of phosphorus are observed in the summer and the fall. Related challenges, well, we need to figure out what drivers are actually responsible for the processing of the decline in nitrogen. Is it a watershed process? Do we have a balance in terms of an ecosystem mass balance? And what are the processes involved with the reduction of the concentration and flux of both nitrogen and phosphorus? And I think that's in a need for a more regional-wide model to understand that, as well as more continuous monitoring down at our NICSAC station. So any questions you might have during the break, I'll be happy to answer.
Thank you, Mark. You're going to be provoking a lot of discussion when it comes to, I think, the fate of that nutrient out in the marine zone later in the day. So I'd like to introduce Tarang Khangaonkar, and I'm proud to be able to pronounce his name. I'm one of the few, but we've collaborated a lot on some interesting projects. And Tarang.
Yes, thanks, Eric. Eric and I serve on the Skagit Climate Consortium, so he's familiar with my last name. And I won't blame you guys if you don't pronounce it exactly right, but it's pronounced Khangaonkar, and he was very close. Okay. All right. So, Eric, thank you for inviting me to present the work that I do. When we spoke, you mentioned that there was interest in finding out what's available for doing research in Bellingham Bay. So, over many years that I've been here, I worked in Bellingham Bay sporadically. Early on, it was related to NPDES type of work related to the GP outfall. And later, we put together a very fine scale model of Bellingham Bay in connection with Bellingham Bay Action Team. The model was developed but was not put to much use. So I'm happy to actually come back to it and show that it still exists, and if researchers want to use it, we can certainly make it available. And then Eric, you also mentioned there was interest in climate change effects and upwelling. So that is some work that we are doing in collaboration with Department of Ecology and EPA related to entire Salish Sea, and Bellingham Bay is part of that Salish Sea. So I thought I would pull out some of those results and share with you. So this slide simply summarizes a model of Salish Sea that we have put together in collaboration with the Department of Ecology and EPA through a National Estuary Program grant. It became clear sort of around 2004 that there were several research groups working in different parts of Puget Sound building their own models, and each model suffered with the problem of not having proper boundary conditions because each basin connected with this adjacent basin and on and on. So we decided to pull together a model that covered entire Salish Sea, but also focused on the challenges that are faced by our agencies. So EPA Ecology, of course, are faced with the challenge of administering Clean Water Act. And then agencies such as NOAA, they need information in connection with Endangered Species Act. And then you have lots of cities, counties, and the tribes who work along the shoreline. So you need a model that can accurately represent the processes that happen along the shorelines, because if there are problems, you're not going to go to middle of Pacific Ocean to fix it. You're going to have to fix your shoreline. So we went through and selected a tool that would allow us to do just those things. It's an unstructured grid model. We have a hydrodynamic component, salts, currents, velocities, intertidal mud flats, and then we have a associated biogeochemical water quality module to simulate parameters such as nutrients, algae growth, dissolved oxygen. And Ecology and EPA folks are also now working on adding sediment diagenesis, decay of organic material in sediment that leads to hypoxia, and ocean acidification issues. So this is a tool that is a work in progress and has already, people have started to apply it at many different estuaries. So most recently, we applied this tool to evaluate what would happen to Puget Sound water quality in the future. What would happen to the water that comes into Puget Sound in the future, and that relates to what happens to Bellingham Bay. So working with Climate Impacts Group at University of Washington, ecology folks, they developed hydrology of rivers all around Puget Sound. What would happen to inflow of water? So the general finding was that in the future, we don't expect the water flow to increase significantly, but the shape of the curve may change. As seen, as seen in the curve for Skagit River, what they found was the peak discharges through snowmelt go away in the future, but instead you have much higher flows throughout the winter period, and the summer flows become low. And those have implications in terms of how the water circulates in various basins. Ecology folks also conducted computation of what sort of pollutant loads we might expect in the future. And they are projecting nearly doubling of pollutant loads through a combination of population growth and changes in our agricultural practices and whatnot. So we plugged in this information into our model. Along with that, we also plugged in the information related to sea level rise. So National Research Council came up with estimates of sea level rise that we may expect for the Pacific Northwest. And depending on which emission scenario you pick, folks are coming up with different sea level rise estimates. So for the purpose of this analysis that I'm going to show, I picked up the extreme case of about 77 centimeters of sea level rise corresponding to the high emission scenario. So if you go back to the theory of estuarine circulation, circulation depends on water depth and salinity gradient. And when I use the term circulation, what I'm talking about is the leftover exchange flow after you average tides out. So on an everyday basis, flood tide brings the tide in, and then ebb tide takes water out. If you average that out, there is a leftover residual flow that enters Puget Sound through Strait of Juan de Fuca, and portion of it goes into Puget Sound. The other flow goes up around Rosario Strait into Strait of Georgia. So our estuary is such that the amount of estuarine exchange flow is nearly 20 times the total river flow comes. It could vary between 15 to 20 depending. So naturally, it's a very well flushed estuary. With the increase in sea level rise, the exchange flow is expected to increase by 4%. And the model also shows that what enters into Puget Sound will increase by about 5%. So we expect in the future that the strength of flow entering into Puget Sound from Pacific Ocean goes up. So purely from flushing perspective, this is a good thing, right? So this is one scenario where future climate change and sea level rise will help to flush Puget Sound out. That would be so if the incoming water was clean. So the problem is that not all parameters in the incoming water are expected to remain at same level. So we looked at salinity. Let's assume salinity does not change. Let's assume salinity stayed the same. More of same salinity water coming in, the concentration remains the same. When you add more of the same thing, the concentration does not change, right? So I pulled out the results from Bellingham Bay near the ecology monitoring station just to look at what it would look like. And we see bottom salinity in that station for future conditions relative to today's conditions look more or less the same. But if you look at salinity in the surface, you see that salinity is dropped a little bit because for this particular scenario, the year 2070 hydrograph that we used was higher in flow compared to the 2006 condition. So we don't know whether that will stay like that or not. We don't think total flow is going to change, but there will be periods where Nooksack River, especially during the winter conditions, is going to deliver more flow than it does currently. So if you build what's known as frequency plot, you can see that all salinity values generally move to the left. So in these surface layers, we expect to see more fresh water in the future, and then the bottom water remains the same. But if you look at other parameters, such as dissolved oxygen or nitrates coming in, analysis of data from this World Ocean Atlas database on the outer coast of Puget Sound shows that dissolved oxygen levels are dropping at a certain rate per year. So we expect that the open boundary near the entrance to Strait of Juan de Fuca will have dissolved oxygen levels about 1.5 milligrams per liter lower than they are today. And if more of that water comes in, you would expect to see that drop in dissolved oxygen. Same is true for the nitrate concentrations. We see the projections are that the 2070 nitrate concentrations will be higher than today's nitrate. So you plug those numbers in, and the model correctly simulates or shows results as expected at the Bellingham station and at all other stations also, that the bottom nitrate concentrations go up. What would you expect with respect to algae? If there is more nutrient loading, you expect that algae would consume it, and you could see harmful algal growth, right? But what we see is that in basins such as Bellingham Bay, there is quite a bit of algae growth and algal consumption. Algae are able to consume that added nitrogen with no difficulty at all. And once again, by summer, nitrate levels are so low that it is once again a nutrient-limited estuary. Okay? Dissolved oxygen in the surface goes up a little bit because of the higher algae growth, but along the bottom, you get a drop in dissolved oxygen. This is without considering decaying of algae. This is just drop in dissolved oxygen because of more lower DO water coming into the estuary. So these are some of the preliminary results. So the tool exists. Bellingham Bay is part of that tool, and I just pulled out some results just to give you a flavor of how the tool may be used to generate quantitative information for whatever research that you might be doing. Another question you asked me to consider was flushing analysis. So we had not had an opportunity to look at Bellingham Bay in isolation. But because Bellingham Bay is part of this overall Puget Sound, we had done numerical flushing analysis. This is a technique whereby you fill up your entire domain with a numerical dye and then let the model run, where the dye is then flushed out through exchange flow and through all the river flows, and then you watch what happens to the concentration after a period of time. This is called E-folding flushing or residence test, where concentration initial value drops to about 37% of its original value. It's just a way of having uniform comparison. So we see that Hood Canal and South Puget Sound take the longest to flush out. Bellingham Bay is somewhere in the middle. According to this analysis, it takes about 194 days. But you have to treat this number, with the proper understanding that this is flushing of Bellingham Bay along with rest of Puget Sound. If we just looked at Bellingham Bay alone, flushed out with whatever surrounding water, the number would probably be lower. And that is a test that can easily be done, but I just didn't have it with me right now. Okay. So moving on to the next part of my presentation, I wanted to once again introduce to you a very high resolution model of Bellingham Bay that we put together in support of the Bellingham Bay Action Team, with Port of Bellingham also involved in that effort. For this model, data was collected at the stations as shown here, specifically for the purpose of providing calibration information. So it included currents, tides, temperature, salinity. We also did a survey at that time. LiDAR data was collected, and Ecology's consultant collected bathymetric cross-section. And you're absolutely right. During that study, we found that this channel was the dominant channel, and this is in 2010. But now you mentioned that it's changed already. Okay. And here are just plots which show calibration information, tides, currents, salinity profiles during different ebb and flow periods. Mostly we are getting calibration accuracy of salinity less than 2 ppt, temperature less than 1.5 degrees, and tidal root mean square within 10 centimeters. That's considered a very, very good quality calibration for this type of models. And here are some animations for us to look at. Normally, oh, there you go. So this is just one tidal cycle. These days, most models are able to generate animations, but I wanted to show this because during the time that the data was collected during this study, we found that there was a plume of fresh water that was entering the study site. And then later, as we completed the Salish Sea Model, we found that plume was connected to the Fraser River. So at that time, it was interesting to see that in the middle of the study, suddenly there was this new source of water. We didn't have that source of water, but it was Fraser River water that was coming and impacting this. But what it shows is ebbing and flooding and intertidal flats being exposed both in Bellingham Bay and Salish Bay. And during that time also, we had a discussion of should we just do Bellingham Bay or should we do this entire region? And as it was mentioned in the morning, Bellingham Bay is the entire region and is connected to Rosario Straits and surrounding straits. And then there was some effort to look at fish migration pathways. And so what we have done is we have connected up the hydrodynamic solution to NOAA's oil spill modeling software. And they use this particle tracking method. I found it useful to release particles like this to see how the water moves around in Bellingham Bay. And then Eric Beamer and others also are thinking that this might be useful for doing experiments related to fish migration pathways and tracking. So these are the tools that are available. And here's my summary slide for discussion. So much is possible just with existing information that we have. We can further look at influence of Fraser River, do more accurate estimates of flushing time if there was interest, or do fish-like particle tracking, that is, provide some movement rules for fish to for the particles to give it more fish-like motion, and then other activities which we need more information, or what I see as research needs are effects of decaying sediments, because I think Jude Apple at one point thought that there could be hypoxia in Bellingham Bay, and then that would certainly need to be looked at in terms of decaying sediments. And of course, ocean acidification is a big issue. So we are in the process of building a ocean acidification module to see what would happen if the acidity of the incoming water were to increase, and how we can mitigate against it through restoration of eelgrass and other such actions. Thank you.
Thank you, Tarang. That was wonderful. Our last speaker in this physical processes session, Jim Johannessen, also known as maybe Mr. Beach from the Pacific Northwest, trying to recover some of our soft beaches. And we think we're going to have about 10 minutes for discussion about what you've heard here after Jim, and certainly more today. And I want to lastly remind everyone about the posters. Liz got me on that. So Jim, thank you.
Okay, thank you, Eric. Good to see such a great turnout here. There's a tremendous interest. That's wonderful. I'm going to show you some of the large-scale shore changes over many years, give you a few examples of a little bit of the data we've been collecting in recent years, show you a few restoration projects, talk about some of the tools where you can get to more enhancement and restoration projects. This is downtown Bellingham, just south and east of the Whatcom Creek mouth. Of course, Whatcom Creek mouth would have been further in, but just to give you an example of sandy beaches right there, close to where Cornwall Avenue is now to your left, going out over made land towards its terminus. Before I get too far into it, I just wanted to give a moment in memory of Maury Schwartz, Professor Emeritus of Western, Dean of Arts and Sciences, passed away about a year ago. I studied under Maury, many others did. They're working on beaches and shorelines around the country and in fact around the world. Maury also used to sit up on the hill in his house here watching Bellingham Bay every evening and watching the progress of some of this more recent actions when it went from red back to blue and green, as Bert commented earlier. Maury actually coined this term net shore drift cells, littoral drift cells, as they're known in many other parts of the world. So we're talking about historic conditions here that we created for the Army Corps of Engineers back in 2007 and this Pisnarp group, Puget Sound Ecosystem Restoration. Maury's students had mapped the drift cells as they are today, and most of eastern Bellingham Bay today is mapped as no appreciable drift. We have changed all that since historic conditions. So we were asked to go back and all around the Sound and make a go at what were the historic drift cells. So as we can see, as we interpreted this, we have what we call a divergent zone. This drift cell that today goes up from Cliffside Beach and Little Squalicum towards the delta, that would have started way back in here, these old bluffs. We thought we had a little drift cell coming out to what was probably near the Whatcom Creek mouth, another drift cell running up towards the Whatcom Creek mouth, even a short reverse cell to what formerly broad sandy beaches in Fairhaven and what some want to call Harris Bay. And then this one's a little trickier out here to interpret. Of course, we've had the railroad since. We probably had some intermittent small amounts of sand and gravel drift to the north. On the other side, we'd still have these drift cells intact on Portage and Lummi Peninsula. Of course, we've seen changes there as well, but not as dramatic as we see in the downtown area. So that's our historic context. Actually, you saw one of these images with Mike Hogan earlier, just trying to show you how quick and how efficient these guys were at doing their job, and appreciate Randy urging us to be a little more efficient in doing our job, undoing some of this. There's our gross shoreline comparison, 2001, the red shoreline, mean high water. We can even see the mean high water way back at the top of the map, as Eric showed you. Now it's advanced all the way down on the Nooksack. Downtown is certainly advanced out. Again, I'm just going to go through this very quickly. Zooming in on the downtown, though, we've had sandy shores all along this reach, all the way up towards town. This was the low water line, so this couple hundred acres of eelgrass, and that's an intertidal that you heard mentioned over here earlier. Notice this old wharf to get to deep water. And as I bring this up, I believe that is that same wharf going out. So you're looking back towards Seahome Hill. So again, that's all our intertidal, now beneath former industrial lands. And even going back in time further, I believe this would have been this shoreline running up in this direction with these sandy and gravel shores here as well. So tremendous amounts of change. Fairhaven, much the same. We used to have the beach underneath Harris Avenue, a spit and a lagoon landward of Harris Avenue here. The old Padden Lagoon was that way. Right now, the Harris Culvert's a tremendous restriction of flow and fish passage. We'd love to get to that next after this current phase of Padden Creek work. We've got restrictions and constraints on all sides down there, so the current project you see is fairly limited in scope, but doing what we can with the fixed boundaries we've been given at the high water line. There's a lot of tools. I'm not sure everybody knows about these. They've been coming out at higher rate lately. This is a good thing. 2007, we had this series of valued ecosystem component white papers on the Pisnarp website. So some of the key species, some of the key habitat types. Management measures for protecting Puget Sound nearshore. 21 ways you can remove bulkheads, you can remove grinds, you can do levee setbacks. There's chapters like that. Feeder bluff mapping in Puget Sound, it's now sound-wide. We've completed that data set just about a year ago. That info is all available through the Ecology website. And then last year, the Marine Shoreline Design Guidelines, how to do more practically, more direct guidance on beach nourishment, on bulkhead removal, the use of large wood for erosion control and habitat, which is a much more limited application, I must say, than some of the others. But those are explained, that's through the WDFW and other websites. So these tools are all out there, they're all online. I want to show you a quick run through something we did a few years ago along with Confluence and Veda from town here. Looking at the Riowan, basically the Whatcom County nearshore. This is the Riowan Nearshore and Estuarine Assessment and Restoration Prioritization. This was done for the city of Bellingham, money that Rene Lacroix put together to fund this through grants, to develop a science-based, user-friendly prioritization tool that will guide protection and restoration efforts in the estuarine and marine nearshore. So this used the ecological value criteria method. It's been used successfully in some other areas, and I'm not going to go into all the methods here, but these were some of the things that were scored: forage fish, herring, eelgrass, freshwater input, proximity to Chinook-bearing streams, and other salmon-bearing streams, some of the primary ones. So it was a large GIS analysis, went through, and it had a course scale needs assessment. We collected all the data we could, assessing process degradation. This is a Pisnerpian language. If you don't speak Pisnerpian, there's a few lexicons online. I'm trying to go low on the acronyms anyway, but so that we got the priority areas identified. It moved to the fine scale assessment. What are the opportunities? So we gathered all the maps and descriptions from things like the Bellingham pilot that was mentioned earlier, Bellingham SMP update, restoration plan, Whatcom SMP update, restoration plan, some work that we did for the Marine Resources Committee, other projects. Got them all together and then went through the scoring criteria and then gave the results in terms of is it restoration, truly restoring process? Is it enhancement, simply trying to get back partway to a process that was there in the past? Or is it simply protection? Keep the good stuff ready and in place. 139 total projects identified. And I'm just going to show you the quick overview of those. And there's points elsewhere in the county. I'm not showing you those. It's hard enough just to show at this scale, bay-wide. But again, we've got the restoration in red, the enhancement in yellow, and the protection in green. So we obviously see lots and lots of yellow enhancement in the more developed areas and some of the other project types in the other areas. This is also online through the City of Bellingham's website. And to zoom in a little bit for you here, we've got, as you would imagine, a whole slew of potential projects with weighting. As the weighting isn't shown here, but there's top priority, highest priority. We looked at the Nooksack estuary in some detail. I'm not showing you that today. Then we had what's realistic in a 3-year time frame, maybe more in a 10-year time frame, complex, larger projects divided separately. The good news is a few of these are already underway, even since this few years since this has been out. Some of these are partially done, some are going to get done further. The data gaps we identified through that study, juvenile salmonid utilization of our nearshore, and good news is there, Eric Beamer will give you some results that has been studied since this time in 2013 today. You'll hear that. What about a vulnerability assessment of these habitat types to climate change? I think there's definitely some work we need to do in that front as well. Not very much underway. Detailed studies of some of our coastal tributaries. We've know more about the river as we should, but we don't know very much about some of these tributaries around the bay and around the county. Data compilation, data for waves and erosion rates would be very useful. I'm not trying to show you some of our erosion data now because we've got it in very localized areas only, certainly not bay-wide, but we don't really have any wave data. We've got a couple months of it that the port paid for a few years ago, but other than that, we don't have any data. There's no stations out there. Okay, so actually you've seen some of these images. Mike Hogan showed you Marine Park, Port of Bellingham owned park. I'm just going to show you that these projects do indeed happen. This is 11 years ago now, several years after we started talking about In Progress, where we were able to take out the armor, put in a beach. This has been doing very well since then. It's won a few awards. We could do more projects like this. It actually took all the way to this winter, though, for it more of a distinct, what we call a two-berm morphology to form some of our big high water storms we had earlier in December. So these projects are very doable, and looking at just a quick snapshot of data from Boulevard Park that was designed and was constructed a little over a year ago. This is an example of some of the data we have for some of these limited sites. So this is surface change from the as-built to year one monitoring. And we see some of these changes are measured in quarter-foot increments. So this has actually gone down by a quarter foot to a half foot, gone down up to 1 foot. The blue areas have risen generally less than 1 foot in that first year. So here's our higher storm berm formed in a few of the bigger events. And then we had just a little bit of lowering, this material essentially moving onshore. Gravel tends to move onshore. It does not move offshore to eelgrass. That's been proven here and elsewhere numerous times. I'm bringing this one up for a little bit of deja vu. This was a slide I put up in 2003 for the Waterfront Futures Group, another one of the many acronyms that has come and gone. The good news is some of these projects identified in a very crude way in these yellow beach potential areas, again, are underway. We helped with some planning for the Cornwall landfill in this area, so we've got large beaches planned for particularly this site, smaller beaches over here, and a much smaller beach than the yellow one here, but we're fitting into these developed shorelines. Unfortunately, we're actually looking at losing beach area right here with some of the cleanup plan, with the riprap plan, some of the removing lots of toxics, lots of debris, lots of armor, but some of that's going to actually lose some beach in this area under the current plans. I think there's definitely room for some more habitat work in the waterway. This is a slide I believe Renee LaCroix put together a few years ago. Under her grant writing and management, a lot of these projects have been happening. I've added a few to this slide in the last, since these was made more than 5 years ago. But the big ones, the big words say projects that are done. The little words are the ones that are slowly in progress. And this is probably not complete. I think I must have forgotten a few shoreline projects. But we were looking at a whole suite of projects all the way around the bay. And I'm not really focusing on the west side, on the reservation side. There has been a good amount of work done out there, a good amount of planning, analysis, and some level of projects, but it's not so much in the management scheme, I think, of most people in this room. So to wrap up with these last two slides, other data gaps besides what you saw from that RIA 1 study, we really don't have wave data to speak of. As I said, we have no monitoring right now of waves in Bellingham Bay whatsoever, and only that very limited amount of data from one particular season. Water level data, same thing. We have water level data at Cherry Point, and we have it in Friday Harbor, we have it in Seattle, but we don't have anything in Bellingham Bay. And that's a very simple, low-cost thing to measure water level, calibrate it, use it to predict events. What are the change events? What are the water levels that are giving us biological or physical responses? We've got some isolated beach monitoring in a few of these projects I showed you. Mostly it runs out in 3 years, and there's never a lot of money to do much analysis. Going back in year 5, going back in year 10, going back in year 15, these things are highly valuable, and then compiling and comparing all those data. We would like to then get into more detail on specific beaches. What is causing sediment transport? What is causing erosion? What is causing accretion? What are the thresholds? We don't have that data around the bay. The forage fish spawning sampling, I know there's been some work started up again, but there's still a lot of data gaps as I see it from the physical side about which beaches are providing good habitat that's being utilized. And of course, as you may hear, the seasonality is so great in these, in those systems. So we do have a lot of work to do. I'm throwing out a few ideas here to think big. One idea of thinking big is when we want to do beach enhancement, We're kind of running out of easily available and environmentally acceptable ways to get gravel and sand from the uplands, and yet we've got millions of cubic yards coming into the Nooksack Delta. We might actually change our thinking a little bit one of these days and grab some of that sand and put it somewhere where it's going to be terribly productive. That's what they do in the rest of the world. We just don't do it in Puget Sound so far. We've got more awareness of habitat issues from the deep water, from the shallow water, but I'm sure that could be done responsibly. In order to have some of this enhancement and restoration, we need to pull back at times. That's pretty hard to do for many, but pulling back in one area while maybe even pushing out in another area or staying neutral is always makes a balanced project. Making enhancement and restoration part of the cleanup projects, the MOTCA projects and others, it's not always easy to do with the regulatory framework and the funding framework, but when the work is getting done, it's time to try to do all the work and not come back later and do a restoration on top of a cleanup. In Cornwall landfill and that area, that there's good direction to try to merge the cleanup with the enhancement. It's a good step right now. We need to keep educating people. We're all here today, but the turnover in residents and in people working in these jobs is higher than we want to think a lot of times. We need to keep at it. Love to streamline some of these permitting processes and such where projects are habitat benefit and have them be a little less of a long road. And I will leave it at that. Thank you for your attention.
We have time for about 10 minutes. Doing pretty good. It might be really helpful to hear from some of the managers who spoke earlier. Does any of what we talked about sort of resonate, raise some flags, provoke some ideas about things you may sort of need, maybe haven't thought of, or maybe think of it now in a little different way, but just toss a few of those items out in just listing them essentially now. We can come back to them a little bit later in the regional perspective and sort of combined thinking, but I'd like to just lead off. I mean, I think we heard one is waves and winds. We're developing a wave model for the bay, but we're not there yet with enough solid measurements to validate a wave model. Yet it does, I didn't mention it in the talk, but with the Nooksack Delta facing directly south-southeast, it's one of the only deltas in the whole Salish Sea that actually faces right into the prevailing winter winds and waves and is able to trap a lot of that material. Very different than the other deltas. But waves are going to be affecting all of us. Colleagues' paper just a couple of years ago assessed the whole U.S. coast shoreline, and for one more foot of sea level rise, our coastal storm surge that we get today every 100 years is going to become a 10-year event. And with 2 feet of water, that same 100-year event is going to become the annual event. So we're going to be dealing with a lot more sort of coastal flooding like we've seen at Boulevard Park and places, and things like that. So throw that one out. But any response from the man?
I think from Lummy's perspective, again, is that we would like to have some assistance on getting the log jams out of the river. But because of this ESA and other things, it's more of a safety factor because of all the stuff that you said on winter storms, early springs, and how the farmers think, because they want to get the water off the land, and then we face it down here at the bottom. But with the problem that we got is that you got to study the jams and its effects. And it gets back to where the point of the tribe anyhow is that we've seen what the cumulative effects are. Because when the rivers in the 50s start coming up, the solution was raise the dikes instead of solving the problems. Now our people that were living down the village, the feds came in and literally told you're moving. And remember, there's the problems that we're facing today in fishing and our way of life and all the siltation that's coming down. And these programs that are set up, a lot of them are voluntary. And then there's one called, what's that one with the Corps where there's setbacks? Programmatic, where they're looking at where they can create setbacks with levees so the fallout can be up where it should be instead of down here. Because people have to understand all this stuff comes down and it blocks up down here and it becomes a safety hazard, as you've seen at people at Lummi Island, not only there, but the residents of the reservation because of the access issues. That's where we need help on the log jams and stuff. But us as Indians, we need scientists, and then we have to study it some more. That's what's frustrating.
Any longer-term modeling of the changes in used to see between the old Nooksack River Delta and the new Nooksack River Delta. I think it's probably given that having been a depositional environment for a long, long time, we're experiencing a net subsidence in a lot of places, except in the new Nooksack Delta portion, the north part of the bay, where we have all that progradation. But it seems like the implications of that have, or there are huge implications for the future of the shellfish harvest on the reservation. And I was just wondering if anybody's done any long-term forecasting.
Yeah, not that I know of yet. We'll put it on the list, though.
Your shellfish harvesting depends upon the water. And right now your bay is acid. 5.5 to 6. You should be at 7.3.
I talked to Gigi Berardi at Huxley, and she said she would like to have her students plant industrial hemp in the polluted soil around the edge of the bay. And the Senate is now considering changing hemp into an agricultural product rather than a drug, which it's not. Can't get high off of it. And it's the best thing in the world for cleaning up soil. It pulls toxins out of the soil. They're even using it in Russia to pull the pollution out of the radioactive waste around the nuclear reactor. And I was wondering if you have any plans to use industrial hemp to help pull the toxins out of the soil in our polluted bay soil.
Yeah, answer that one.
I'm not sure if the researchers here are best to answer that, but maybe some of the managers that spoke earlier could mention that later at one of the breaks. I don't think it's been proposed yet as a soft armoring approach or a water quality improvement approach yet, but one more question and we have to move on.
Okay, I just wanted to comment, it's really helpful to hear the data gaps and what the work is that needs to be done. But for those of us who work in a grant-funded world, just saying Jim says that this needs to be done isn't necessarily going to work. So maybe Sue, as part of the proceedings, if we could kind of capture what's been recommended as gaps so that there's something we can refer to as we move forward, because I've seen some pieces that are things that we may be able to take on in some of the groups I'm working in, but we need to have it documented that this is a known data gap in Bellingham Bay so that we can use that to go forth and try to find funding to get it done.
Can you all include some comments on your evaluation forms?
And we're going to break for lunch right now, and we're going to cut it just a bit short, so come back at 12:40.
You've been watching a presentation from the State of the Bay Symposium held in January 2015 in Bellingham, Washington. If you'd like to see the other 6 presentations from this symposium, please visit the City of Bellingham's YouTube site, www.youtube.com/cityofbehamwa.